What's up, everybody? It's Dan from Sage Math Tutoring, and here with a video where I'm going to cover an entire review sheet for a student. And the student is allowed to have a note card, and therefore, with every slide, anytime we come across information that could go on the note card, I'm just going to kind of highlight that. All right, so let's get started. Looking at this one, simplify the exponential expression. So I actually was working with the student yesterday, and I had mentioned various exponent rules. So here's one. We know that in this case, we can add the exponents. When it comes to this situation, we can subtract the exponents. So this would be rule letter B. For this scenario where you have sort of a product raised to a power, you could, in a sense, distribute the exponent to both of them. In this case, we could do the same. Okay. What else? Anytime we are raising a power to a power, so if we had something like that, you can actually multiply the exponents. It's also true that anything to the 0 power is just 1. It's also true that anytime you have a negative exponent, you could kind of think of it as though it's a 2-story building and you switch floors. Okay, that's a way of thinking about it. So what this would become, therefore, is the x to the third on the bottom, and then maybe you could, have that 1 on the top. So there'd be a 1 on the top. Okay. So that is the case with rule letter G. Rule letter H. It's related to rule letter G. Let's say we have 10 over x to the negative 2. Well, any time you have a negative exponent, once again, you can think of it as a 2-story building, and whatever has a negative exponent actually switches floors, so it goes up to the top floor. And in this case, what would that look like? Well, that would look like 10 times x squared, because, of course, the 10 is already on the top floor. And if you choose to still see this as a 2-story building, that's fine. However, most teachers would expect you to just write 10x squared here. You don't need to really write the 1 underneath. But nonetheless, it's helpful to see these scenarios through the lens as if they were 2-story buildings. Okay, looking at this. This is one that I did mention to my student yesterday, but upon looking at the review sheet, I see that this is going to come up. And that is any time you have a thing raised to a fraction, we'll call this the blue 2, and we will call this the green 3. Okay, so anytime you have that scenario, you can put a radical on it. Okay, and it's really 2 possibilities. The first possibility is such that the blue 2 goes here and the green 3 goes here. Another possibility is such that the blue 2 goes here, but we actually put parentheses around the whole thing, and the green 3 goes there. So that is the case with this. Now, for the record, for my student watching, anytime you see a radical with nothing written in the index, that means that there is secretly a 2 there. Okay, so it wouldn't be customary to write 2 here. Usually we would just leave it blank. Okay, nonetheless, I wanted to illustrate that this blue 2 that was indeed here in the denominator, well, it gets transferred to the index. Okay. But anyway, that's the pattern. Now, of course, what does that mean? Well, that means that you should probably put, this stuff in the no card. Or at the very least, pick the ones that you feel like you might have a hard time remembering and put those in the note card, right? So these could go in the note card, right? All of that if you want. So that's the thing. Now, as it pertains to um, solving the problems, which is what we're supposed to do, let's see. Simplify that. Okay, so what I would do is I would start with the big picture. I would ask myself, what is the big picture of what's happening here? Well, this is a fraction being raised to an exponent. I know that's negative. I know there's shenanigans happening in here, but again, what is the big picture? The big picture, it's a fraction raised to an exponent. That reminds me of rule letter D. What does rule letter D tell us to do? Rule letter D tells us to apply the exponent to the entire top and the entire bottom. So that's what we're going to do. We're going to apply the exponent to the entire top, in parentheses, and the entire bottom. What goes in the top? Well, that was a thing that said that. Well, it's in the bottom. That's this. Okay, cool. Now, you investigate one thing at a time, looking at the numerator. What is this? What rule does that remind us of? Hopefully, we're recognizing that is a product being raised to a power. Well, what is that? That's rule letter C. So that means you apply that exponent to all of the things. So we have 5 to the negative 4. Now, let's be careful. This is x to the third to the negative 4, right? And then down here, what do we have? Well, we have a power raised to another power. What does that remind us of? Well, that's rule letter E. What does rule letter E tell us to do? Multiply the exponents, right? So therefore, we have y to the negative 8, okay? Then investigating further. This is going to go down below soon, okay? But before we do anything like that, let's just investigate this because order of operations would suggest just simplify the entire numerator first and then simplify the entire denominator and then kind of see what you have after that. So we will keep this for now. And what does this remind us of? This is a power raised to another power. As I had mentioned before, that is indeed rule letter E. So we are going to be multiplying these exponents. So that's going to become x to the negative 12 all over y to the negative 8. Now, what did I say about negative exponents? Well, negative exponents are such that if it's on the top, it goes to the bottom and the exponent turns positive. If the negative exponent's on the bottom, we bring it up to the top and the exponent becomes positive. So that means that these are just going to get switched, right? So the final answer would feature y to the positive 8 all over 5 to the positive 4 and then x to the 12. Now, it's probably the case that your teacher would be happy with many students making it this far. However, it's such that you want to process this. Anytime you have a number that's raised to a particular power, well, you actually can find out what that is. That's 5 times 5 times 5 times 5. And I do believe that's 625. So this would be your final answer. Okay. So that is how you do that one. Now, problem number 2 is a little different than problem number 1 because problem number 2 has x's over x's and y's over y's and numbers over numbers. That wasn't happening here. We had a number, but there was no number down here. We had an x, but there was no x down here. We had a y, but there was no y up here. So this is a slightly different situation. And the way I like to go about these is I count my cast of characters, how many characters are in the cast of characters. And what I mean by that is, what kind of bases are we dealing with? Well, we are dealing with numbers. We're dealing with base called x. We're dealing with a base called y. So that's 3 characters. And whenever I see that it's 3 characters, I immediately set up my silo system. All right, so there are 3 silos. And by the way, we're going to keep going, but this is all assuming that this numerator is as simplified as could be. And this is all assuming that this denominator is simplified as well. Now, there's really not much else we could do here in terms of what to do on the top. There's not much else we could do here, really. So we are ready to pull the trigger. Now, what goes in the first silo? What goes in the first silo are the numbers. What goes in the next silo? X to the 6 all over x to the 5. What goes in the next one? Y to the 12 all over y to the negative 8. Okay, then you take your time, okay? Take your time, painstakingly even. Uh, Submit to the fact that this might be tedious and you just go line by line and no rush whatsoever. Process each silo separately. What is 21 over 3? Well, let's be clear. That is, of course, a 7. But let's keep it in fraction form. I'm going to say for the silo method, keep it in fraction form until the very end. This right here, I know my student knows that that's going to turn into just an X. However, let's take advantage, and I would suggest taking advantage of rule letter B that says anytime you have this, you can subtract them. So I would actually suggest, believe it or not, for these problems, do the intermediate step, and you're going to see why in a moment. What is the intermediate step? This is the intermediate step, okay? What's the intermediate step for the y's? Well, it's going to be the same. Now, you might be getting an idea as to why I'm doing the intermediate step, because look, that's a minus negative, right? We want to be very meticulous about that. We want to be very careful. So this is 7 over 1. What is x to the 6 minus 5? Well, that's x to the 1. I know my student knew that. Let's put our little two-story situation there. This is going to be y to the 12 plus 8. I know we know that that's this. And we could put our little two-story situation underneath. And then at this point, you look at it and you're like, okay, that's sort of as simplified as could be. That's as simplified as could be, right? That's kind of simplified, right? And by the way, there are no negative exponents. So the moment you see everything is as simplified as could be, we have these nice little fractions. And also, you see that there are no negative exponents, then you're ready to go ahead and multiply straight across. Now, multiplying fractions means you multiply the numerators straight across and you multiply the denominator straight across. With regards to the numerators, we end up with 7xy to the 20. And that's that. Simplify using properties of exponents. Okay, well, this is going to feature probably part A. What is it called? Rule letter A. This is probably going to feature rule letter I. But what else? Yeah, that's probably it. Okay. So rule letter A says that anytime you're multiplying two numbers with the same base, you can just add the exponents. I am going to take advantage of the fact that multiplication is commutative, which means it doesn't matter which order we multiply things in. So we have 2 times 5. I'm going to put the numbers with the numbers. And then we have x to the 3/4 times x to the 2/3, okay? And the reason for that is because, we could just clearly see, oh, obviously that's a 10, right? And then it's going to be x to the, we have 3/4 plus 2/3, right? 3/4 plus 2/3. What is that? Well, we can at least represent this intermediate step in the name of not rushing things, right? Now, let's analyze what is 3/4 plus 2/3. I mean, we'll go on a separate mission real quick and we'll ask ourselves, well, what is that? What is this? Hopefully by now we know that we want a common denominator. You can multiply 4 by 3 to get 12, and you can multiply 3 by 4 to get 12, because 12 is a good candidate for a common denominator. So hopefully we recognize that this is a thing. Therefore, up top, we have 9 over 12 plus, 8 over 12. And what is that? I guess that would be 17 over 12, which is kind of funny. So we have that, right? So then it's going to be 10 times x to the 17 over 12. Now, it's possible that the teacher actually does not want the fraction exponent and instead wants students to take advantage of rule letter I, which says, anytime you have a fractional exponent, you could either turn it into this situation or this situation. So I am tempted to do that. Let's see. What would that look like? Well, that would look like 10. It's definitely going to be a radical. And then you have an x. I'll put the 17 here and the 12 here. Okay. So that should work unless I'm crazy. All right. Add or subtract terms whenever possible. Okay. Simplifying radicals. There's a couple ways of going about this. However, based on what I'm seeing in the rest of the review sheet, I think the following is going to be a good idea. So there is sort of a rule also that says that any time you are adding or subtracting two things that have the same exponent part, or radical part, I should say, you can almost treat that like it's this situation, where you would literally just combine like terms, right? I mean, that's what this would become. It would become 7x, right? Notice how the x we kind of left the x alone, right? And we just added the coefficients. Well, it's the same with this. So it would be 7 radical x. Now, maybe that's something that could go in the note card also, right? This principle, generally speaking, could go in the note card. So that's a thing. Let's see. That's something to keep in mind. Therefore, the goal, partly with this next problem, is to basically make it so that the radical parts are the same. That way you could combine these. Now, there is an opportunity to make this thing into a radical 3. And that's what your teacher is expecting you to realize. So let's analyze one way of going about it. Okay, one way of going about it. Many students like the prime factorization, where first of all, you can acknowledge that prime numbers would be 2, 3, 5, 7, 11, 13. Okay. Prime numbers are numbers that are only divisible by themselves and 1. Okay. And interestingly, the first prime number is 2. It also happens to be the only even prime number. So what you could do is you could take your 27 and do a prime factorization. You could ask yourself, does 2 go into 27? No. Does 3 go into 27? Yes. So that's 3, and then it's 3 times 9, right? Now, 3 is already prime, so we kind of leave that alone. And then we ask, okay, does 2 go into 9? No. Does 3 go into 9? Yes. So then you would break that up into 3, and now you have prime numbers at the tips of the branches. It's like an upside down tree, right? At the tips of the branches, we have nothing but prime numbers. Now, a way of going about this that some teachers do is they will acknowledge that there is sort of a little 2 here, right? As I said before, there's also a 2 here. There's a little 2 there. So what you're looking for is pairs, okay? You are looking for pairs of matches, right? So we have a pair of 3s here. Now, what that tells you when you circle this is that tells you that only one of those guys is getting out. Now, whoever is not in a pair is stuck under the radical. So I'll say that again. Because there's a 2 here, we're looking for pairs. By the way, if there was a 3 here, we'd be looking for groups of 3 of the same, okay? But since there's a little 2 here, we're looking for pairs. We found one, okay? And anytime there's a pair, that means that only one of them gets out. Who's left? This thing. So that means that we could sort of rewrite this situation such that one of the 3's gets out, right? And who's left in there? A 3. Okay. And then maybe we'll keep the 2 here. What is this? That's minus 24 root 3. Notice how the root 3's are the same, and due to the previously mentioned principle, that is going to turn into negative 19 root 3. Okay, looking at problem number 5. Well, you could sort of do the same thing. Notice how there are 3's here, right? And therefore, we're looking for groups of 3, just like I said. So let's remind ourselves of what the prime numbers are. I do think that's helpful when analyzing how to simplify these, right? So let's begin by analyzing 320. So we have 320, and then we ask ourselves, does 2 go into 320? Yes. So we go 2, and then what would that be? 160. And then we ask ourselves, does 2 go into 160? Yes. So that would be 2 times 80. And then we ask ourselves, does 2 go into 80? Yes. So that would be 2 times 40. And I think you see that that would be true. The following would be true. This would be true. And then you're actually done because it's the case that that's a prime number and all of these are prime numbers. So now we're looking for batches of 3, are we not? Because there is this 3 here. So to find batches of 3, well, clearly we have a batch of 3 right here. And we also have a batch of 3 right here. Now, please remember that what that means is only one of those gets out. Only one of these gets out. And who's left? The 5. The 5 is left. So we have an 8 times one of these 2's times one of these 2's. And who's left? The 5. Okay, so that is the case with that. Looking at analyzing 135 in a similar manner. We ask ourselves, does 2 go into 135? No. So then we look at the next one. Does 3 go into 135? Yes. Upon inspection, you would see that 3 does go into 135. For my student watching, by the way, you might wonder, how did I know that so quickly, that 3 goes into 135? Well, there is a trick that you probably learned at some point that says if you add these digits together and that number is divisible by 3, well, then this number is divisible by 3. So what do I mean by that? 5 plus 3 is 8, plus 1 is 9. Is 9 divisible by 3? Yes. So therefore, 135 is divisible by 3. So then we split this into 3. 3 goes into that 45 times. So then we look at the 45. We say, does 3 go into 45? Yes. So 3 times 15. Okay. And then we look at the 15. Does 3 go into 15? Yes. 3 times 5. Right. And then we're done because all of those tips of the branches happen to be prime. Then we can circle the groups of 3. And as you know, this means one of these gets out. We're left with this one. So then we would have 3 and then root 5. Now, by the way, I should have put a 3 here. Okay, let's simplify further. What is 8 times 2 times 2? Well, that is 32. Cube root of 5 plus 3 cube root of 5. Due to the previously mentioned principle, that will be 35 times the cube root of 5. So that's that. Cool. Okay, use the quotient rule to simplify the expression. Right. Okay, so there is a principle that says the following. If you have x times radical y, well, that's really radical xy. Similarly, if you have radical x over radical y, you could treat that as this. Now, you could also go vice versa. If you start here, you could always split it into that. And if you start here, you could always split it into that. So it kind of depends on your goal. All right. Now, this, of course, is something that could totally go in the note card. Okay. So that's that. Well, let's call this rule number one. This is rule number two. This is an opportunity to use rule number two because we can kind of drape a radical over the whole thing. And the reason why we might want to do that is because there is this opportunity to sort of simplify that which is inside the radical first. You could kind of deal with that first, right? Now, I already mentioned how to do that, right? So off to the side, what would that be? That would be this. Now, if you want to go about it in painstaking detail, you could realize there are two characters in the cast of characters, therefore two silos. One of the silos gets numbers, the other one does not. 120 over 6, what does that become? That really just becomes 20, but secretly there is a 1 underneath it. With regards to this, I think we understand that's x to the 4 minus 1. Okay, cool. What does that become? Well, that's really 20 over 1. And then we have x to the, 3, secretly over 1. And then next thing you know, multiply straight across, you have 20x to the third. All right. So really, this is just radical 20x to the third. But then you should know how to sort of simplify this situation. Now, really, I would say with regards to the red 20, you can go ahead and do that prime factorization. Does 2 go into 20? Yes, 2 times 10. Does 2 go into 10? Yes, 2 times 5. And we have, of course, this pair. So we know that 2 is going to get out, but a 5 is going to be left in there. Now, you can kind of do something similar with the x to the third. So the x to the third, you could split that into x times x times x, and then you could circle the pairs, okay? And that means one of those is going to get out, and this poor x is going to be left inside. For my student watching, this is the process that I would recommend at this stage in the game. I have a process for these that I like better, but this is a simple enough situation where you can kind of get away with this process here. So as it pertains to the number, that red 20, who gets out? Well, according to this information, a 2 gets out. So let's process that. As it pertains to the x to the third, who gets out? Well, one of these x's gets out. So let's process that. As it pertains to the number, who got left inside? Well, that was a 5. So that's left. As it pertains to the x cubed, who gets left inside? That is an x. So we have that. All right, so that is the answer to that one. All right, rationalizing the denominator. Basically, mathematicians decided that they consider it rude to have radicals in the denominator. And one way you might have to deal with that is if there's a binomial down here. Now, a binomial is two terms that are separated by addition or subtraction. Okay, so I'll say that again. A binomial is two terms that are separated by either addition or subtraction. Now, whenever you have a binomial on the bottom and you have a radical, you should multiply both the top and the bottom by a very special number. And that very special number is called the conjugate. And the conjugate is the exact same thing, except the opposite operation. So it's going to be a plus. So up top, we will have to deal with this soon. Now, on the bottom, though, the reason why mathematicians love multiplying by the conjugate is because it results in a very specific pattern. And that specific pattern is such that it's going to be something squared minus something squared. So for my student watching, I would encourage my student to remember that. Okay, it's going to be something squared times something squared. And what is going to be the first thing? Well, it's this number, 9. What is going to be the second thing? This radical 3. So literally put a radical 3 in there. Now, let's take our time. We can process the top. I think we understand. We end up with a 45 plus 5 radical 3. Down below, 9 squared, 81, obviously. Minus, okay, what is this? Well, this exponent of 2 cancels the radical symbol. So we end up with 81 minus 3. So then what does that become? 45 plus 5 root 3 all over. What is 81 minus 3? 78. And I think we're done. Yeah, I think we're done with that. There's not really anything else we could do. I mean, you might be tempted to factor out a GCF 5 here, but it wouldn't cancel with anything down here. So we're kind of stuck with this situation. So I think we're happy. Now, notice how this is the same thing as this. I mean, this thing equals this, but we represented this thing in a way that's not rude because it's rude to have radicals on the bottom. We messed with it, so there's no longer a radical on the bottom. Okay. What goes on the note card? I don't know. Maybe literally put this in the note card if you're allowed to put actual problems in the note card, because I feel like you can kind of see what you're doing there, and that will remind you of what to do next time. Okay, so looking at this one, express the perimeter of the rectangle as a simplified radical expression. Okay, very easy. So I think my student watching understands that if that's 3 plus radical 50, well, that's going to be the same. I think my student understands if that's 7 plus radical 2, well, that's going to be the same. So let's go ahead and do that, okay? Now, there are fancier, more sophisticated ways of going about this that might include, the formula of the perimeter and whatever, but I don't care. Let's keep it very simple. It is the case that the perimeter is nothing more than adding all those side lengths, right? So that's going to be 7 plus radical 2 plus 3 plus radical 50. And then it's going to be plus the same thing again, right? So that's that. Now, the thing your teacher wants y'all to catch, though, is the fact that this radical 2 thing can't really be simplified any further. However, the radical 50 can be simplified further. So therefore, let's go on our side mission. We have a radical 50. What does that turn into? Well, does 2 go into 50? Yes. Does 2 go into 25? No. Does 3 go into 25? No. Does 5 go into 25? Yes. So that becomes this. Do we have a pair? Yes. We do have a pair. It's right here. So one of these is going to get out. In fact, let's just kind of write it up here just to keep it organized. So we have a 5 getting out, but we have a 2 left over. So therefore, anytime, let's be very clear, anytime we see a radical 50, we can replace it with this. Okay. Well, let's do that now, right? We can replace all the radical 50s with what we just said, right? 5 radical 2. So 5 radical 2, 5 radical 2. And you might be wondering, well, why did we do that? I mean, that seems like a lot of work for nothing. But it's not, because now this can get combined with this. Before, you couldn't. The radical 2, the radicand was a 2 here, and the radicand was a 50 here. So you actually couldn't combine these, but now we can actually combine these. So everything I'm underlining in blue is such that it can be combined. Okay. Anything I'm underlining in green can also be combined. Those are like terms because those are all constants. So let's process the green underlined ones. 7 plus 3 is clearly 10. And then there's another 7 plus 3. So that's going to be a 20. So it's going to be 20 plus something. Now let's be very careful. That's 1 radical 2. This is 5 radical 2. 1 radical 2 plus 5 radical 2 is 6 radical 2. Okay, so I'll kind of write that here. When you combine these, that becomes 6 radical 2. When you combine these, that becomes 6 radical 2. And what does 6 radical 2 plus 6 radical 2 become? Well, that would become 12 radical 2. So that is what the teacher's looking for there. Which of the following expressions are equivalent? Let's see. Well, for this one here, you might want to do that whole simplifying thing, right? So you have your prime numbers, 5, 7, 11, dot, 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 because they keep going. So if we were to process 16, does 2 go into 16? Yes. Does 2 go into 8? Yes. Does 2 go into 4? Yes. And then do we have any groups of 4? Yeah, actually, we have this group of 4 right here. So that tells you that one of these is going to get out, right? So we could process that in a moment. Now we also have this x to the 7, this blue x to the 7. Well, hopefully my student watching is recognizing, well, that's just 7 x's, right? That's just 7 of these, all kind of getting multiplied together. And we are looking for groups of 4. Do we have groups of 4? Well, yes, we have this group of 4, but that's it, right? So as it pertains to the 16, a 2 is going to get out and nothing is going to be left. As it pertains to the x to the 7, one of these x's is going to get out and these 3 x's are going to be left inside, right? So let's process the number. 2 gets out and nothing is left in there. And let's process the x to the 7. One of these x's gets out. And then there is going to be 3 x's multiplied to each other left under the radical symbol. Okay, so hopefully that makes sense. Okay, so when they say Roman numeral 2 is this, what they really mean is that it's this. Okay, so these are the same. Looking at Roman numeral 3, I would do the thing where I would tilt that fraction such that there's a radical. So we have x, the 4 goes here, and then maybe the 7 goes there. So let's investigate. Well, as it pertains to Roman numeral 3, hopefully we're seeing that we have an x to the 7th. Now, we had that before under the radical. We already decided it turns into this situation, which means 1 x gets out, and then 3 of these are left. So let's actually do that right now. We'll take an x out, and then 3 are left. So what does that mean? Well, that means this yellow box 1, Roman numeral 3, is equal to this green box 1, Roman numeral 2. Am I wrong? I feel like they're equal. So therefore, Roman numeral 2 is equivalent to Roman numeral 3. So 2 and 3, 2 and 3. There it is. Okay. Looking at this, any time you're multiplying a binomial times a trinomial, a trinomial is a group of three terms separated by either addition or subtraction. So I'll say that one more time. A trinomial is a group of three terms, each separated by either addition or subtraction. All right. Now, anytime you have a binomial times a trinomial, I would do the box method. So for my student watching, this might want to go in the note card. With the box method, you can write the trinomial across the top and write the binomial down the side. And you end up with 3 columns and 4 rows. And all you do is multiply the things. 9x times x squared, that is 9x cubed. For my student watching, pause the video, think about that if need be. Then we have 9x times negative 3x. Well, that's obviously negative 27x squared. Then we have 9x times 1. That's 9x. Then we have negative 1 times x squared. That's negative x squared. We have negative 1 times negative 3x. That's positive 3x. We have negative 1 times 1. That's negative 1. Now, very often, not always, but very often, we're going to have diagonal relationships that represent like terms. The green circled things are like terms, and the yellow circled things are like terms. So therefore, writing the whole thing out, it would be 9x cubed, and then combining like terms, negative x squared plus negative 27x squared. That's negative 28x squared. Combining these like terms, 3x plus 9x is 12x. So that will be a plus 12x. And then negative 1 is just negative 1. And then you're actually done. That's the product there. Okay, so the box method's really good for that. You know, maybe for your maybe for the note card, you do this, right? Put all that in the note card. I don't know. Is that smart? That might be smart. Put that in the note card, right? So this here, now there's sort of a fancy schmancy way of doing it, but I would rather students, and maybe this is dumb, but I'm kind of a fan of people not having as much mental baggage. And the reality is this is just 7x minus 6 times another 7x minus 6. And then hopefully my student watching remembers that that's just a FOIL situation, right? Now, what does the F in FOIL mean? The F in FOIL means first times first. So 7x times 7x is 49x squared. What does the O in FOIL means? That means outer. So that's the two outside things. 7x times negative 6, that's negative 42x. What does the I mean? The I stands for inner. What are the two inner things? These. So that's going to be a negative 42x also. What is the L stand for? L stands for last. So that's going to be negative 6 times negative 6, aka positive 36. Very often, you will have the opportunity to combine like terms in the middle. So that would be 49x squared minus 84x plus 36. Now, there is another fancier way of going about that, but I would say just remember this is just this thing times itself, and therefore you can apply FOIL. When do you apply FOIL, by the way? You apply FOIL when you're multiplying a binomial times another binomial. Not to be confused with the above situation where we had a binomial times a trinomial. If it's a binomial times a trinomial, use this box method. If it's a binomial times another binomial, use FOIL. Okay, let's see. Write a polynomial in standard form that represents the area of the shaded region. Okay, so this is sort of like a donut shaped situation. We want the area of the darkened region. Whenever you have a donut type of area problem, um, very often it's going to be a matter of just having the taking the area of the larger thing and subtracting the area of the smaller thing. So you could imagine it's going to be the area of the whole big box, right? It's going to be the area of the whole big box minus the area of the little white box. Okay. Well, what is the area of the whole big box? The area of the whole big box, let's keep it very general, is length times width, right? And then what's the area of the small box? Well, that's going to be the length times width of the small box. We'll put a little s down here because it's just like, it's a different length and a different width. So that's the length of the small box, width of the small box. Well, what is the length times width of the large box? Well, that's just these things getting multiplied together, right? So it's going to be that. What is the length times width of the small box? Well, that is, of course, these things getting multiplied together. Okay, so that is FOIL. That's a FOIL situation for both of them. So first times first is x squared. Outer times outer is 8x. Inner times inner is 3x. Last times last is 24. Now, here's where you have to really be on your game. You will be subtracting the entire quantity of whatever this becomes. So you must, when you're subtracting like this, for my student watching, this product, you have to throw brackets around it, around the product. So what is the product? Well, x times x is x squared. The outer times outer gives us a 2x. The inner times inner gives us another 2x. The last times last gives us a 4. Now let's go ahead and simplify. We have like terms, like terms. Over here, we have like terms, like terms. So, of course, we could do x squared plus 11x plus 24 minus x squared plus 4x plus 4. At that point, the whole reason why we threw brackets around the thing, you know, was because we have to distribute. So as a result of that, we end up with this scenario where it's minus x squared minus 4x minus 4. These will cancel. The like terms that are left over would be the blue underlined terms and the green underlined terms. As it pertains to the blue underlined terms, we're looking at 7x. As it pertains to the green underlined terms, we are looking at positive 20. So that is the answer. With that, we satisfy what they wanted. Write a polynomial in standard form that represents the area of the shaded region. Well, here you go. Factor out the greatest common factor. Okay, what is the greatest common factor of 21x to the fourth, this and that? Well, for factoring out the greatest common factor, you need to remember you're dealing with numbers, first of all. So you have to take that into account, but you're also dealing with variables, right? So you're going to have to take the green underlined variables into account. With regards to the red underlined numbers, what's the GCF of those? Well, the GCF of those is 3. Okay, so you can write a 3. As it pertains to the green underlined variables, what is the GCF of those? Well, the GCF of variables will always be the smallest exponent one. So it's going to be x squared. And then you could put parentheses there. So 3 times what gives me a 21? Well, that would be a 7. X squared times what would give me an x to the fourth? Well, that would be an x squared. 3 times what would give me a negative 9? Well, that would be a negative 3. You could say x squared times what would give me an x to the third? Well, that would be an x. 3 times what number would give me a positive 15? Well, that would be a positive 5. And then finally, x squared times what variable would give me an x squared? Well, that would just be 1, so we could leave it alone like that. All right, so now we did that properly. I will say that, the way that I just described that last part might be clunky for some, but just know another way of thinking about it is you could say, okay, well, here's my GCF. I factored that out in the beginning. Okay. And you could be like, okay, well, what's 21 divided by 3? 7. What's x to the fourth divided by x to the 2? X to the 2, right? What's negative 9 divided by 3? Negative 3, right? You could do it that way too. Okay, so that's factoring out the GCF. Factor the trinomial. Many teachers nowadays are seemingly fans of this X method, where you have this kind of blue 16 and you have this green 63. Now, the green 63 goes up here and the blue 16 goes down here. Now, you could also say that there's an invisible green 1 there. So you can say it's really 1 times the green 63. Okay. Uh, that it might come up later, to be honest. So 1 times 63, well, that's just 63, right? So let's keep it simple for now. We'll call that a yellow 63 for now. What you're doing is you're asking yourself what two numbers multiply to 63 but happen to add to 16. Well, it is the case that 9 and 7 would do the trick, right? So 9 times 7 gives you a 63, and 9 plus 7 gives you a 16. So when it comes to something like this, where you just have a green leading coefficient of 1 in the front, in other words, it's not like a 3 in the front or a 10 in the front. If you just have a 1 in the front here, you can then just get away with just being like, oh, okay, cool. Well, it's going to be x plus 9 and x plus 7, right? These right here. Boom. Okay, so that's how you do that. So that's that. Okay, yeah, exactly. So this is what I was talking about before. This is also an X method. However, with this, we have a leading coefficient other than 1. So the way that I like to do is you could multiply these together, and that is going to give you your number that goes on the top. Okay, so we'll make that the yellow number. Now, 5 times 42 is 210. And then we have this blue negative 37, and that's going to go down below. And then you ask yourself, what two numbers multiply to positive 210 but add to negative 37? That is sort of annoying, I have to be honest, because 210 does have a lot of factors. Now, we're looking for factors of 210 that would also add to negative 37. Now, let's think about it. Positive factor times another positive factor would give me a positive 210. But if you add a positive plus a positive, you're not going to get a negative. So we must take into account the fact that a negative factor times another negative factor, well, that would give us a positive 210. And a negative number plus another negative number, well, that would give me a negative number. So we need to maybe in the beginning take into account the fact that whatever the pairs of factors are, we want them both to be negative. So I'm actually going to draw some negative symbols down the line here, just so I don't forget that, okay? Now, we might need, a lot of numbers. We might need to really investigate this, but let's go ahead and investigate it. What two numbers multiply to 210? Well, negative 1 and negative 210. That would multiply to positive 210. What else? Does 2 go into 210? Yeah, 2 times 105. Does 3 go into 210? Well, yes, actually, 3 times 70. Does 4 go into 210? No. Does 5 go into 210? Yes, it turns out that 5 times 42, and we kind of knew that because we had multiplied these. Now, once again, notice how I have the negatives here, because negative 5 times negative 42 would give me a positive 210 also. Now, we need to keep going because negative 1 plus negative 210 does not equal negative 37. We need to keep going because negative 2 plus negative 105 does not equal negative 37. If you were to add these, it wouldn't give you negative 37. So we need to keep going. We need to keep investigating. What other two numbers, when you multiply them, will give you a 210? Well, we already tried 5. Well, what about 6? Well, as it turns out, 6 would go into 210. 6 times 35. Now, we need to look at it. Is it the case that negative 6 plus negative 35 gives us a negative 37? No, unfortunately. So we need to keep going. What else goes into 210? Does 7 go into 210? Yeah. 7 times 30 would do it, and negative 7 times negative 30 would do it. And I think you're probably noticing we hit the jackpot. These are the two numbers that not only multiply together and become a positive 210, but if you added negative 7 plus negative 30, you would get a negative 37. So you can put those numbers here, negative 7 and negative 30. Now, here's the part where there's a lot of divergence between the way teachers will do things. What I would strongly recommend here is I would factor it much in the same way that I did before. What did I do before when I had a 9 and a 7? Well, I just threw them in the parentheses and then I called it a day. Well, in a sense, you're going to kind of do that right now. You're going to imagine it's a normal situation where you would just say x minus 7 times x minus 30. But then you must remember you're not done. And the reason you're not done is because you have this pesky red 5 out front. So, what do you do with that? Well, the way I like to do this is I put the red 5 here. I know that's a weird move, but this is called slide and divide. A lot of teachers do like this. In my opinion, this is the best way to go about this situation. Anytime you have a leading coefficient other than 1, you might want to do this, okay, as long as you can't factor out a 5 in the beginning. So we're here. Then you look at this, you ask yourself, can I make this nicer? Can I simplify 7 over 5? No, right? So that means this 5 goes out front. And what does that become? Well, that would become the following. It would become 5x minus 7. So it's almost like we took that red 5 and put it out front here, and everything else stayed the same. Okay? Now that's kind of a weird move, but you get used to it with practice. Looking at the next parentheses, first question, can I make this nicer? Yeah, 30 over 5 is just 6. So you know what? We're going to write x minus 6, and then we're done. Okay? Now you might be wondering, well, that seems kind of tedious. Well, first of all, the reason it's tedious is because there's a lot of factors of 210. I'd say this is actually an unusual situation where they gave us this yellow, 210 number that happened to have like a ton of factors. So that's one reason why it took kind of long. This process does not take long. Okay. For example, I'll just demonstrate. Imagine we had 3x squared. Let's call this a negative 6. We have a plus 7x. I'll show you how quickly I could do this. Done. Okay, so as you can see, that does not take long, all right? This right here. I think what I would do, what I would suggest to my student is treat it like it's like a thing that just has X's in it, and then factor that first, and then make a slight adjustment at the end. So we put the 28 up top. We put the 11 down here. What two numbers multiply to 28 but add to 11? Well, that would be 7 and 4. So you can just factor it like this first. X plus 7, x plus 4. But then you remember, oh, but there was this red y that was bothering us. That shouldn't be a problem. You could put the red y here at the end. And I think that would work because if you were to FOIL that, you would indeed find out that it would just become this again. For example, the last times last, well, that's 28y squared. So that is the strong recommendation to my student watching to do something like that. Okay. Now, what could go on the no card? I would represent this process in the no card, this whole slide and divide situation. I would strongly consider throwing that in there. I feel like my student watching, you're probably going to remember that. feel like for my student watching, you're probably going to remember this. Just remember you got to distribute the negative. Okay, so for this section, it actually features quite a bit that could go on the note card. Now, let's kind of cut to the chase in that regard, actually. So, one concept that we could definitely use is something called the difference between two squares and how to factor the difference between two squares. So, if you have some perfect square minus another perfect square, you could sort of get clear on whatever your so-called A is, and you could get clear on what your so-called B is, and then you just kind of plug it into the structure, and then you will have factored it. Now, an example of this could be something like 25x squared minus 4, and the A will always be the square root of the first thing. Okay, that's what your A will always be. Now, in this case, the square root of 25x squared is 5x. So that's important that we recognize that. Now, the B will always be the square root of whatever that second term is. And I think we can all see that that's going to be 2. So this would therefore be nothing more than plugging all of that into the structure. It would become 5x plus 2 and then 5x minus 2. So that's something that we should be getting good at. Okay, so that's that. Let's see, what else could go on the note card? It could also be on the note card the difference between two cubes and the sum of two cubes. So that would look like the following. Let me just finish this. A plus B, A minus B. So the difference between two cubes looks like this, and the sum of two cubes looks like this. Now, notice how it is always going to be a relatively short parentheses and a big parentheses. And since you have a note card, maybe you don't even need to memorize this, but there is like a way of remembering the sort of signs. Okay, so it's always going to be AB. It's always going to be B squared. It's always going to be this, basically. But then there's an acronym called SOAP, where this is going to be the same, the opposite, and always positive. Same, opposite, always positive. But either way, for my student watching, just copy this on your note card, okay? So that is going to be important. Now, in this case, the so-called A is going to be the cube root of whatever A cubed is, and the so-called B is going to be the cube root of whatever B cubed is. So that's kind of similar to what we just did before. Now, that's all relevant. So let's take a look at this one. This is asking us to factor the difference between two squares. Let's get this near our situation so we can clearly see what's going on. Do you remember how I said the A is going to be the square root of the first term, and the B is going to be the square root of the second term? Well, the square root of the second term is easy. That's just 4. And the square root of the first term is actually x squared. So hopefully my student watching recognizes that x squared times itself would give you x to the 4th, okay? So therefore, when figuring this out, it's going to be a plus b times a minus b, and that is, of course, x squared plus 4 and x squared minus 4. Now, the teacher is being very sneaky because you might think that you're done. But then when you look at it, you have the difference between two perfect squares here also, okay? So we have to keep factoring at least this part here. Now, let's go above it. I think in this case, we can realize that the so-called A is the square root of x squared, and the so-called B is the square root of 4. Square root of x squared is x, square root of 4 is 2. So this green parentheses part gets split into two other parentheses. Now, this part stays the same. There's nothing we can do with this part, but this other part becomes x plus 2 and x minus 2 because of the red 2 and because of the yellow x, right? Hopefully that makes sense, and we are done factoring that. So as it pertains to the next problem, it's clearly going to be the sum of two cubes. So we're going to get that structure ready and waiting for us right now. So let's take a look. We have clearly a perfect cube here plus another perfect cube. And once again, a in this case would be the cube root of the first term, and b would be the cube root of the second term. The cube root of 27 is like asking what times itself 3 times would give us 27. Well, that would be 3, because let's think about it. 3 times 3 times 3 is 27. The cube root of this one is 4x. Okay. What times itself 3 times would give you a 64? Well, that would be a 4. 4 times 4 times 4 would give you a 64. What times itself 3 times would give you an x cubed? That would be x. X times x times x gives you an x cubed. Now, once you have figured out what your A and your B is, well, the rest is kind of easy, right? Because you could just kind of compare it to the structure that we have, right? So you have a little parenthesis and a big parenthesis. What goes in the little parentheses? Well, that would be the 4x plus 3. Then you have to be careful. So let's acknowledge this is going to be something squared here minus something times something plus something squared. So I'm actually going to do parentheses. Now, I have experience, so I know that this is going to be useful, and I would encourage that. So what goes in the first parentheses? Well, clearly we know that we have the A and the B. We kind of already figured that out, right? So let's take a look at that. What goes in the first parentheses? Well, that red 4x, right? Now, what goes here? The 4x and the 3. However, I'm going to put the 3 over here so that the x is kind of on the right. What goes in this parenthesis? Well, clearly 3 squared. Hopefully that's clear. Then what do we have? We have 4x plus 3. And you should be careful. 16 squared, well, that is, or 4x squared, that's 16x squared. Let's be very careful here. Minus 12x plus 9. Okay, and that is the answer to that one. Okay, they wanted us to factor using the formula for the sum or difference of two cubes. Well, we use the sum of two cubes, so we're done with that. Factoring by grouping. Okay, when you want to factor by grouping, I'm going to be a proponent of rewriting this such that it's descending order of exponents. So in other words, I'm going to put x cubed and then 2x squared and then 7x and then plus 14. And I just would rather do it that way because I'm using foresight to see how this will go. Should you always do this? Yeah, sure. Always do this and see how it goes. Okay. And if for some reason it doesn't go well, then try factoring by grouping the way it was. Okay, so what do? You focus on one pair of terms at a time. And then you ask yourself, what is the greatest common factor of the blue bracket pair? Well, the greatest common factor of the blue bracket pair is x squared. So x squared times x would give me x cubed, and x squared times 2 would give me 2x squared. So these terms are divisible by x squared. So then we have to ask ourselves, x squared times what number would give me x cubed? Well, that would be x. And then we ask ourselves, x squared times what number would give me a positive 2x squared? Well, that would be a plus 2. All right, so far so good. It seems like things are working out okay. Then you perform the same analysis over here. Now, this is positive, so it's going to be a plus. And then you ask yourself, what is the greatest common factor here? Well, that would be positive 7, and then we have x plus 2. Notice how the red parentheses match. Now, by the way, that's a sign that you're doing everything correctly. That's a sign that factoring by grouping is indeed working, because the final answer, or at least close to the final answer, is going to consist of two parentheses. Now, one of the parentheses is that repeat one. So that will be x plus 2. Now, what's the other parentheses? Well, the other parentheses consists of all the other stuff, all the blue stuff. So that's going to be x squared plus 7. And then you must look at it and you must ask yourself, am I done? Can I factor this any further? Well, the answer is no. And then you look at this and you ask yourself, can I factor this any further? And the answer is no. That's not factorable any further. So we are done with that one. Um, mm, mm, mm. Okay, factor completely. This is their way of saying, whenever you're trying to factor stuff, you might want to double check and see if there's a greatest common factor, sort of in the beginning of the process. Now, let's be very clear. There was no GCF that goes into all four of these terms. There was no GCF that goes into these. There's no number that goes into 64x cubed and 27 at the same time. There's also no GCF here. But I will tell you, there is a GCF here. And that happens to be 2. It's the case that all of these terms are indeed divisible by 2. So let's go ahead and factor out a 2. So 2 times what would give me a 2x squared? Well, that would be x squared. 2 times what would give me a negative 2x? Well, that would be a negative x. 2 times what would give me a negative 12? Well, that would be a negative 6. Then you can focus only on the red parentheses part. With regards to the red parentheses part, you can put your negative 6 up here. That's based off of this blue negative 6. And then you can put your green negative 1 down here. And then you ask yourself what two numbers multiply to negative 6 but happen to add to negative 1. And I think we understand that that would be a negative 3 and a positive 2. So therefore, we can sort of factor the red parentheses accordingly. It will be x, it will be x. And we're going to have a minus 3, and we're going to have a plus 2. Okay, so to recap, we factored out the 2 first. It's right here. Then we look at the red parentheses, and then we decided to factor the red parentheses according to the previously mentioned methods. And then the next thing you know, we have this. And then you just look at it and you ask yourself, can this be factored any further? The answer is no. So we leave it alone. Okay, find all numbers that must be excluded from the domain of this one. So, okay, looking here, when they want you to know what must be excluded from the domain, I will tell you right now, more often than not, that means set the bottom equal to 0 and solve, and acknowledge that whatever those solutions are, those are not in the domain, okay? But let's just dive in. Just know, once again, for my student watching, when they ask you a question like this, where you're trying to find the numbers that must be excluded from the domain, the first step is to set the bottom equal to 0 and solve. Well, we could probably factor this. Let's take a look. Using that big X, we would have a 35 here, we would have a 12 here, And yeah, so you would have a 7 and a 5 because 7 times 5 is 35 and 7 plus 5 is 12. So therefore, it would be an x. We would have an x and we would have a plus 7 and a plus 5. Now, typically when you're solving these, like if it's an actual equation, unlike this was not an equation. If it's an equation and it's set equal to 0, you actually have to go further and set this thing equal to 0. Okay, so that's going to be set equal to 0. And we will need to solve that. That would be a matter of subtracting 7 from both sides. Similarly, we must set this thing equal to 0. Okay, and we must solve that. And we would realize that x is equal to -5. So what this means is if x was -7 here, it would force the whole bottom part to equal 0. And we also know that if x was -5 and we plugged it in here, it would force the whole bottom part to equal 0. And therefore, the fraction would be undefined. This whole fraction would be undefined because there's a 0 on the bottom. Now, you're not allowed to have undefined fractions in math land. Okay. In math land, you're not allowed to have undefined fractions. You're not allowed to have zeros in the denominator. Okay. So therefore, these must be excluded. And the reason they're excluded is because they would cause the bottom to be 0. All right. So that's that. What else? What else? What else? Okay. That's it for that. Okay, multiply or divide as indicated. Okay, so whenever you're presented with something like this, you should immediately just factor everything. So what does this become? This becomes x, and if you were to do the x method, that would become +7 plus 6. If you were to do the big X method, that would become 7 and 6, would be minus and plus. If you were to do the difference between two squares, this would be x plus 7 times x minus 7. And if you were to do the regular x method here, that would be x, that would be x, that would be a 7, that would be a 6, but it would be a plus and it would be a minus there. Okay, so that is the first step. Now, for my student watching, I used all the previously mentioned strategies to find this factorization, this factorization, this factorization, this factorization. Now, what I am sort of a fan of is, now you don't have to necessarily do this part, but I like to do what I have to ignore everything else. In fact, I'm gonna show you exactly what I do with these. So what I do exactly with these is I then cross these out because to me they're distracting. And then I pay attention. Can I do any cancellations between the top and the bottom? And by the way, I'm also taking into account these diagonal relationships. Well, clearly this x plus 7 cancels with that x plus 7. This x plus 6 cancels with that x plus 6. And this blue x minus 7 cancels with that blue x minus 7. So what does that leave? That leaves an x plus 7 over an x minus 6. So this becomes just x plus 7 over x minus 6. Hopefully that makes sense. That is actually the answer to that one. Over here, they are saying divided. Just know that anytime they say big rational expression divided by some other rational expression, that's code for keep, change, flip first. So we're going to go ahead and keep this part, and we're going to change the division symbol into multiplication, and then we're going to flip the other part. So this part's going to go on top, this part's going to go on the bottom. So that will be the first step. If you have to remind yourself of that by writing it in your note card, feel free. With regards to the factorization here, we're going to have some factorization, right? This one's going to be a little different. Let's do a little boundary line. So over here, this is going to be x plus 2, x plus 4. This is going to be x, this is going to be x, this is going to be plus 2, plus 9. Over here, it's going to be x plus 9. x plus 9. Now, this one's a little different because you cannot factor this using the x method because this is a binomial. Now, they both feature an x in it. Now, that just means you can factor out an x, so you would have an x plus 4 there, okay? Now, once again, if you're going to do it with my style, you can get rid of all this because it's kind of sort of distracting. And notice that the x plus 2 cancels with that x plus 2. We have an x plus 4 canceling with that x plus 4. We have this blue x plus 9 canceling with one of those. Now, who's left? We have to be careful. X plus 9 is left, but it's also the case that this x is left. So therefore, this whole thing ends up equaling x plus 9 over x, and then you're done. Okay, so for these, you must get a common denominator. Hopefully my student remembers back in the day, back in the old school math days, you got to get a common denominator. Now, how do you choose a common denominator if you're going to subtract these? Well, you have to find what's called the least common denominator. And very often, that's going to be, well, it is definitely going to be the least common multiple of these two denominators. And in this case, it's going to be a matter of considering the product of these, okay? So, in other words, this is the denominator that you're going to want to be under each fraction, okay? Now, in order to force this denominator to be this one, what's missing? Well, we need an x minus 4. So therefore, you can go ahead and multiply it by x minus 4. But you're not allowed to just multiply the bottom by x minus 4. You have to also multiply the top by x minus 4. Then you can look at this one. You can ask yourself, what's missing if we want to turn this denominator into this? Well, clearly it's missing an x plus 4. So you can multiply the bottom by an x plus 4, but you also have to multiply the top by an x plus 4. Now, what does that result in? Well, it's certainly going to result in a denominator. Well, it's going to result in two fractions, right? It's going to result in two fractions. And they're both going to have the common denominator, which was sort of the point, of doing what we did, right? So we have that common denominator, which is a beautiful thing. But then over here, I think hopefully you can understand you could distribute the 5 in there. So that would become 5x minus 20. And then hopefully you're acknowledging you could distribute the 2 here. So that would become 2x plus 8. And this is still subtraction, right? So let me just make that very clear. So that is subtraction. Now we must be very careful because it is true that this will consolidate into a single fraction that does indeed have the common denominator that we wanted, right? However, we need to be very meticulous because it will be 5x minus 2 minus the entire quantity of 2x plus 8. Now, that is hugely important. Many students in the class are going to forget to put brackets around this, so you must remember to put brackets there. It's the case that the negative will then distribute. Hopefully that's clear. As a result of that, we would have 5x minus 2 plus or minus 2x, and then that's minus 8, and that's all over our common denominator that we had from before. And then we could go further. So it's the case that this is still on the bottom. We would have 3x minus 10. Now, it's likely the case that the teacher would then want you to go ahead and multiply this out on the bottom. So we would therefore have x squared minus 16. Okay. Now you might be wondering, how did I know so quickly what that is? Well, first of all, you could FOIL it. You could do first times first, outer times outer, inner times inner. That's a way of going about it. However, you could also acknowledge that this is, that whole difference between two squares situation. It's just that I did it backwards. Okay. So I'm acknowledging that this is of the form a plus b times a minus b, and that turns into a squared minus b squared. So x plus 4 times x minus 4, well, that turns into x squared minus 4 squared, and 4 squared is 16. So that's that. All right, add or subtract as indicated. So when adding and subtracting the imaginary number I, you can treat it as a variable. The thing to keep an eye on, however, a thing to keep your eye on is if you ever end up with an I squared, then you just kind of turn that into a negative one. But you might have to mess with these first a little bit before you end up with an I squared. I would save that sort of towards the end, converting any I squareds to a negative one. I would save that move towards the end. However, right here, this is nothing more than treating I as though it's just like a variable, like X. So you can drop the parentheses here. And the reason is because there's an invisible positive one that gets distributed in there. And then after distributing, you always drop the parentheses. It's the case that there's a negative that gets distributed there and there. So this would become plus 2 minus I. This red underline situation is a like term situation. The green underline situation is a like term situation. So let's combine the like terms. We would have 7 plus 2I. And believe it or not, you're actually done. So that's as far as you can go with that. Notice how there are no I squareds, so we don't have to worry about doing this. This, however, will be relevant for the next one, certainly. So let's once again remember that this is a binomial times a binomial. Therefore, we could do FOIL. Okay. Now, that means first times first, and hopefully we're seeing that that would become negative 24. The O stands for outer times outer. Hopefully we're seeing that that would become a negative 12I. The I stands for inner. Hopefully we're seeing that that would become a positive 8I. And then finally, the L stands for last times last. Hopefully we're seeing that would be a positive 4I squared. And then we have negative 24. It's the case that these are like terms, so that will become negative, 4I, I guess? And then we have plus 4I squared. However, any time you see an I squared, you could always replace it with a negative 1. So in fact, we're going to do that right now. So that is a negative 1. And simplifying further, I think we all agree that the situation on the right-hand side would become minus 4. As a result, we then end up with these as like terms, and then we would have negative 28 minus 4I. And that's as far as you could take that one. Okay, divide and express the result in standard form. So typically they don't like when you have an I on the bottom. And it's very similar to what you'd have to do if there was a radical on the bottom. If there's an I on the bottom, you have to get rid of the I that's on the bottom. And the way that you do that is you multiply the binomial that's on the bottom by what's called the conjugate. And the conjugate, as I explained before, I think, is the same thing on the ends, except it's the opposite operation in the middle. Now, you might be wondering, why in the world would we ever do that? Well, it's because of the pattern of a squared minus b squared. Hopefully, we're remembering that a squared minus b squared is really equal to a plus b times a minus b, and also vice versa. If you have something in this blue a plus b times a minus b structure, well, it could turn in to that. Well, that is this. You have something plus something times the first thing minus the second thing, right? It's the same structure. So therefore, it's safe to say that the bottom part, we'll just kind of rewrite the top part for now. Okay, we'll rewrite the top part as just this. And we'll deal with that, later, right? But as far as the bottom part, that will be something squared minus something squared, namely the first thing squared minus this, this thing, right? The 4I. That is going to get squared over here. Hopefully that makes sense. Pause the video, by the way, if you have to. So anyway, as a result of that, I think we agree that this would get distributed into the things that would become 2I. Then you would have negative 8I squared. And let's investigate the bottom. 1 squared is just 1. Now, what is 4I squared? You have to be careful. It's 4I times 4I, right? Wouldn't that be 16I? So that would be 16i squared. I should have said 16i squared. That's going to be 16i squared. Oh, look, we have an I squared. We have an I squared. What does that mean? That means that you can turn that into a -1, right? So we have -1 here. We have a 1 minus 16 times -1. Let's kind of bring it over here. On the top, I think we would agree that it's 2i plus 8. On the bottom, I think we would agree that would become 1 plus 16. And then that would become 2i plus 8 all over 17. And what the teacher is probably looking for, because there's this mentioning of standard form. So what that's code for is turn it into something that looks like this, okay? That's a complex number. That's the standard form of a complex number, where you have this sort of real part and you have this imaginary part right here. Well, one way of getting closer to that is to split this so that it's 2i over 17 plus 8 over 17. And if we want to make sure we're getting on the teacher's good side, you can switch the order to make it so that the real part comes in the beginning and the imaginary part is at the end, and maybe have the I kind of off to the side like this. So the I was on the top before, but you could also write it off to the side like this. And just notice how this blue box answer sort of resembles this standard form. So that should make the teacher happy. Looking at 28. So what goes in the note card, by the way? I squared equals -1. You could say that. You could have a representation of multiplying, this bottom part by the conjugate to kind of remind yourself of what's involved there. So those are options. With regards to 28, perform the indicated operation, write the result in standard form. Okay, so the moment you see that there's a negative underneath the radical, guess what? You can get away with pulling an I out and then turning it into a positive 80 on the inside. Similarly, this would become 2i, and then we have a 20. I would say do that right away. Then it's going to be a matter of processing this blue 80 and then processing the yellow 20. As far as processing the blue 80, we can do the thing we were doing before. So prime factorization would suggest all of this, right? And what are we looking for? That's a 2 in the index because it's the square root. So we're looking for pairs, right? We're looking for pairs. We have a pair of 2 here. We have a pair of 2s here. So remember, any time there's a pair of 2s or a pair of anything, only one of those gets out. So we will have a 2 that gets out from this pair and a 2 that gets out from this pair. And the poor 5 is going to be left under the radical. So what does that look like? Well, that looks like a 5i times 2 times another 2. And then the poor 5 is left underneath. I'll make that blue. So processing the yellow 20, it's the case that this just turns into that. I think we can see we have one pair of 2s. That means only one of those 2s is going to get out. So we therefore have plus 2i times one of those 2s. And then who's left? The poor 5 is left in there. Let's clean these terms up. Hopefully we can see 2 times 2 is 4. And this 4 times that 5 would be a 20. So we have a 20i radical 5. Over here, we have this 2 times this 2. That is most definitely a 4. So we have a 4i times a radical 5. Now, here is something interesting. Let's remember that if we had 20x plus 4x, well, that would just become 24x. I mean, we all know that, right? So in other words, if you have 20 times some number here, plus 4 times the same number, well, it would be 24 times that number, okay? Well, that is what we have here. We have 20 times some number, plus 4 times that same number. So that's going to be 24 times that number, right? Now, in your final answer, do you need to write those parentheses? No, you don't need to write that. I just drew those parentheses to illustrate the concepts. So this should be the final answer there. Hopefully that makes sense. That is as simplified as could be. Solve the equation by factoring. Okay, well, if they want us to solve this by factoring, first of all, this is a quadratic trinomial in that there's an x squared term, there's an x term, and there's a constant. When dealing with quadratic trinomials that are like that, you must set them equal to 0. So it would be x squared minus 39x and then minus 5, because we would have to, subtract 5 from both sides, right, to make a 0 here. We're really forcing this side to be a 0. Then you can do the process that I had talked about before, where you find the magic number. The magic number would be 40. You can always bust out that big X. You put the negative 40 here. You put the negative 39 here. You ask yourself what two numbers multiplied to negative 40 but happen to add to negative 39. I think we can see that would probably be a 40 and a 1, and it would be a negative 40, right? Because negative 40 times 1 is negative 40. Negative 40 plus 1 is negative 39. Then, if you're going to do it the way that I was saying before, which I prefer, you could set this equal to 0, and then you could just say, okay, x minus 40, and then x plus 1, right? The minus 40 comes from here, okay? And the plus 1 comes from there, right? So that yellow one. But then you must remember that there was this obnoxious green 8 that was in front the whole time, so we should put that here, okay? Now, you then look at it and you ask yourself, can this be made nicer? Yes, it can. That could become x minus 5. You look at this, you ask yourself, can this be made nicer? It cannot. So in that case, the green 8 goes here, and then everything else stays the same. So it's like we took this 8, we just put it out front, and then it becomes that. Now, this whole thing still equals 0. What do you do in this situation? Well, you set this equal to 0 and solve. What do you do with this one? You set this equal to 0 and solve. Now, this one is going to become x equals 5, and this one is going to become x equals negative 1 over 8. And those are your answers. For my student watching, go through the motions with this. I think you understand you'd have to subtract 1 from both sides, and then you would end up dividing by 8. But double check that, make sure you agree. All right, looking at this, solve the equation by the square root property. Okay, so that's just their way of saying, make sure that the constants on one side, let's put it this way. This is their way of saying whatever is being squared, make sure that thing is by itself on one side of the equal sign. Well, that's already the case. They were kind enough to make it that way for us, where this is the thing that's being squared, and it is indeed all by itself. Now, what that means is you can hit it with the move. What's the move? The move is to take the square root of both sides. Notice how I put a little plus minus on this side. Okay. Now, why did we do that? Because this blue square root symbol cancels this 2, and the next thing you know, you have 2x minus 5. And that's going to equal plus minus the square root of 49. I think we understand that that is 7. Now, the problem is that we still need to solve for x, and it's already getting weird because it's like a plus minus 7. What I would recommend in that moment is to separate this into two separate equations. The first equation is 2x minus 5 equals positive 7, and the next equation is 2x minus 5 equals negative 7. As it pertains to the left-hand equation, I think we agree we could add 5 to both sides. Next thing you know, you have a 12. Divide both sides by 2. Next thing you know, you have a 6. I think we agree on the right-hand equation, you could add 5 to both sides. Next thing you know, you would have a negative 2. Divide both sides by 2. You would end up with a negative 1. Hopefully that makes sense. Those are the answers to that one. Let me just take a look. Do I like this? Negative 2. Yes, I do like that. Okay, so that definitely works. All right. What do you put in the note card? anything that represents the process. So for my student watching, any move that I made that you feel like you might need a reminder of, find a way to represent it here. Okay, that's my advice. So that is that one. Okay, solve the equation by completing the square. Completing the square is a very specific process. The first step is to send the constant over to the other side. How do we do that? Well, we would subtract 3 from both sides. So now the constant is over here. Then you add the magic number, or the magic number as it pertains to this. I think many teachers, including your teacher, calls it C. Okay, so you're going to find this new number that we're going to introduce into the situation. You might be remembering from my student watching that that's going to be a matter of focusing on the red 10. And what you do is you divide 10 by 2, and then you take that and you square it, and it becomes a 25. So that is going to be the number that you put there. Okay. So over here, I think we can all see that's clearly going to become a 22. Now, what happens here? Well, the whole reason we even did this in the first place is because this right here can be factored. What does it factor into? It factors into something squared, namely x, and then you pause and you ask yourself, what is this middle coefficient divided by 2? Well, first of all, it's a positive number. So it's a positive 10 divided by 2. What is that? Well, that's a 5. It's a positive 5. So you're right, plus 5. Okay? Then you still need to get the x by itself. It would be a matter of doing the move. And the move is to square root both sides. Next thing you know, you have an x plus 5 for previously mentioned reasons. You have a plus minus radical 22. I do not believe that can be simplified any further. The only factors of 22 are 2 and 11. And there's no pairs of any factors to take out. So you are stuck with that. At this point, I think we acknowledge that our goal is still to get the red x by itself, right? We need to get that red x by itself. Well, we have to get rid of this positive 5. My student watching, I'm sure, knows you must subtract 5 from both sides. As a result of that, you have the red x by itself, which is a beautiful thing. However, you're probably going to want to put that 5 here, that negative 5 there, and then you have the situation there. Okay, so this whole thing turns into that. Believe it or not, that is the answer. Now let's be clear. This is really 2 solutions, right? You have negative 5 plus radical 22, and you have negative 5 minus radical 22. Now, what could go in the note card? The note card could feature, I don't know, an example of that process. I don't think that that's a bad idea. Okay, here's my note card. So let's see. Let's see what's up. Solve the equation using the quadratic formula. Well, I would definitely put the quadratic formula in the note card. So quadratic formula would be x equals negative b plus minus radical b squared minus 4 times a times c. I would definitely put that in the note card. And just keep in mind, that's a structure that you can use when the equation is written like that, okay, where it's set equal to 0, it's in descending order of exponents, and you have your a, right, which is there and there. You have your b, hopefully you're remembering how that works, and then you have your yellow c, and it would be there. So that is a beautiful thing for the note card. And we'll use it. We're going to use it right now. Let's keep it handy for us, right? Keep it near us. Cool. So amazing. What's your A? Your A is 1. What's your B? Your B is 14. What's your C? Your C is 65. So plugging it into the structure, X equals. Now, I'm a fan of doing empty parentheses first. You don't have to do it that way, but I strongly recommend it. So what's the B? The B is the 14. So that goes here and here. What's the A? The A is the 1. So that goes there and there. What's the C? The C is the 65. So what does that become? Well, that would become negative 14 plus minus. 14 squared, I believe, is 196. Minus 4 times 65, which is 260. We will deal with that later. 2 times 1 is 2. Okay. What does that become? Negative 14 plus minus. Okay, what's 196 minus 260? That would be negative 64. Then we have a 2. Now, hopefully, my student watching is remembering anytime you have a negative radical, just pull the I out immediately. Okay, just pull it out. And then we can look at it further. We can say, oh, okay, well, what is radical 64? What is that? Well, that's 8, right? So that's going to be 8i. For my student watching, you may have already caught that, but I still am a fan of the moment you see that negative number under the radical, just pull the I out first. At this point, you can acknowledge, and I would acknowledge, that this is really secretly negative 14 over 2 plus minus 8i over 2. Now, let's look at this. Why is that? Okay, well, this is a common denominator. Let's say we were to go in reverse and we wanted to add these together. Well, what would you do with the common denominator? You would just keep it, wouldn't you? You wouldn't change it. But what would you do? You would add the numerators, you know what I mean? Or subtract the numerators. There's a minus sign, right? So you are allowed to kind of split the denominator amongst the two terms. And the reason for that is because now you can simplify. This becomes a 7, that becomes a 1. This becomes a 4, that becomes a 1. And then the next thing you know, you have a negative 7 plus minus 4i. And that is the answer that the teacher would like. Okay. Over here, compute the discriminant, then determine the number and type of solutions for the given equation. So the rules are as follows with discriminants. Hopefully my student remembers that there are 3 pieces of information to remember, okay? One of them has to do with this equaling 0. Another one has to do with it being less than 0. Another one has to do with it being greater than 0. Now, if it's the case that it is equaling 0, then that is one real solution. If it's the case that it's less than 0, there are no real solutions. If it's the case that b squared minus 4ac is greater than 0, then there are 2 real solutions. So you must find out what's going on here. Well, your so-called A is a 1, your so-called B happens to be a 6, your so-called C happens to be an 8. I think we agree that that will be something squared minus 4 times something. Isn't that the structure of this here on the left? We're just going to find out what happens when we plug in the information. Well, B is 6, A is 1, and C is 8. And let's find out what happens. 6 squared is 36. That's going to be minus 32. That ends up being 4, which is positive. So that would be corresponding with the bottom row scenario. So we are looking at 2 real solutions. You might want to literally write 2 real solutions for that. As it pertains to this, they're trying to trick you because this is all weird looking. Notice how this was nice and neat. It was set equal to 0. Your teacher is challenging you to remember that in order to use this whole rule, well, the whole thing needs to be set equal to 0 in the first place. How can we do that? I think you agree we could add the 6x to both sides. I think you agree we could add the 7 to both sides. As a result of that, it would become 2x squared plus 6x plus 7 equals 0. Next thing you know, you have an A equals 2, a B equals 6, a C equals 7. Let's put all this to the test. Once again, I like to use the empty parentheses. What is the A? The A is a 2. What is the C? The C is a 7. What is the B? The B is a 6. We are looking at 36 minus 8 times 7, which happens to be 56. I don't care what that is. It's like negative 20. But I didn't care because I saw that it was negative. I think you probably agree we're dealing with the middle row, and we are indeed dealing with no real solutions. Now, I will tell you, I probably should have said this. They want to know the number and type of solutions. There are no real solutions, but that implies that there are 2 imaginary solutions. So I am pretty sure the teacher is going to want you to say that also. Okay. So that's that. Cool. Danny tries to factor by grouping and does that. Okay. Well, let's see what he did. You're supposed to focus on one pair of terms at a time. We have the blue bracket pair. Did he handle that correctly? He took out a 5x squared, and that's a 3x, and that is a 4. So that works. He should have taken out, first of all, anytime this third term is negative, that's a sign that you're supposed to take out a negative, okay? Um, so that is a mistake already. But it's also the case that the GCF here would be -6, I think, okay? Not +2, okay? So remember, the idea with factoring by grouping is you want to take out the greatest common factor, not just a common factor, but the greatest common factor. So we're happy with this, but what he should have done is he should have done the other part differently. So what this should have been would be -6, and then he would have had a 3x. -6 times what gives you -24? Well, that would be a +4. And by the way, that would have been a sign that we're doing things correctly, because hopefully my student watching remembers when you're factoring by grouping, which is this specific way of factoring, when you're factoring by grouping, the moment you see that the parenthesis matches, right? The blue parentheses here matches the blue parentheses here, that means that you're doing things correctly. Now, it is asking us to factor the problem correctly, so we're already kind of getting ahead of ourselves. Let's actually finish this right now. It is the case that the situation would then turn into the actual blue parentheses part, right, which is the repeat part, as one of the factors. But then what's the other thing? Well, it will be the 5x squared and that -6 part, right? In other words, the other parentheses is going to feature all the other stuff, okay? Then we look at this and we ask ourselves, can this be factored more? No, it cannot. It's not like it's the difference between two squares. This is not a perfect square. 5 is not a perfect square. That's not a perfect square. 3x plus 4, that cannot be factored any further either. So we are actually fully factored there. What is the mistake? Okay, I guess we have to use our language. Describe the mistake. He did not factor out the GCF from the second pair of terms. Right? This 2 is not the GCF of the second pair of terms. All right, so hopefully that makes sense. That is that one. Okay, well, this looks like a total blast. Let's see. Use the above graph of the function to answer the following questions. Use interval notation where appropriate. The domain, my student watching hopefully remembers, the domain is asking how far left is this thing going and how far right is this thing going? And are there any x values that are missing? Well, this thing is certainly going to the left forever, and this thing is certainly going to the right forever, and it's continuous throughout the whole thing. In other words, I could trace it without having to lift my pencil. So that's a sign that it goes to the left forever and it goes to the right forever, and we can use interval notation. The range is asking how far down is it going, and then how far up is it going, and whether or not there are any breaks that we need to worry about. Well, this thing, once again, is continuous, so we do not need to worry about any breaks, but we do need to ask ourselves, what's the lowest y value that's presented here? In other words, how low does this graph get? Well, the graph only goes so low as to the y value of -1. So that is the first thing. And then how high does it go? Well, it gets kind of high over here. It gets up to the y value of 2 here. But you know what? It gets even higher over here. It gets up to the y value of 3 there. So we can say this thing goes from -1 to 3, and those numbers are included. So we throw brackets around them. For my student watching, this is a little bit different than what we did the other day. Um, this is such that it doesn't go up to infinity and it doesn't go down to infinity, right? The lowest number is literally the y value of -1, and the highest y value that this thing hits is 3. It's happening right there. So please be on your game when it comes to that. Where is this thing increasing? Well, it's going to be increasing anywhere your skateboarder is going uphill. Uphill. Okay, well, where is it going uphill? It's going uphill here. It's going uphill here. Now, when they ask for the intervals over which it's increasing, it wants you to only pay attention to the x values over which it's increasing. So it's increasing on the blue area, but I'm going to use a blue marker to denote the the x values where that's taking place. Hopefully we can see that it's taking place over these x values, right? And over these x values. All right, now I understand that can be confusing, but for my student watching, just know, okay, it's increasing. Skateboarder's going uphill here. Skateboarder is going uphill here. So on the x-axis, where is that represented? That's represented here. And by the way, forever in that direction, right? And it's represented here. So we have this first part to denote, and that goes from -infinity up to -2, okay? Parentheses, parentheses. Why? Because he's not actually increasing or going uphill at the x value of -2. Uh, at the x value of -2, he's neither going uphill nor downhill because there's this pointy part. That's why we put a parentheses around that, okay? Now, where else is the skateboarder going uphill? The skateboarder is going uphill here as well. What are the x values involved there? Well, that would be from 2, right, to 4. Okay, parentheses, parentheses for the same reasons. And math teachers love the union symbol, so you might want to stick the union symbol in between these. Now, for my student watching, these are not to be confused with points. These are intervals over which the graph is increasing. Where is it decreasing? In other words, where is the skateboarder going downhill, right? Going downhill. Well, that's happening in this red area. That's happening in this red area. Skateboarder is going downhill over the red area. On the x-axis, where is that? Well, that's this section, and that is this section forever in that direction. Let's focus on the left-hand section first. I think we can see that's clearly between -2 and -1, parentheses, parentheses. And then the other red decreasing section would be going from 4 to infinity. And then we have a union in between. Hopefully that makes sense. When they say constant intervals, what they mean is where is the skateboarder just cruising across a gymnasium floor, flat surface. I think we can all see that's happening here, okay? Over which x values is that occurring? I think we can all see that's over this green portion. And therefore, the interval goes from -1 all the way to 2, and we throw parentheses around it. Okay, what are the x-intercepts? Okay, well, let me get rid of some of the markings. The x-intercepts appear at the yellow dots. Hopefully we agree with that. This one, I guess we are just going to have to estimate what's going on there. Actually, there is a way of knowing for sure. But would the teacher expect that? Yeah. Hmm. Well, x-intercepts are clearly at -4, comma 0, right? That's one of them. And these are points, by the way, so I'm going to put a comma in between them. The one on the right is clearly 3, comma 0. And this one right here is negative 1.3 repeating, comma 0. And you might be wondering, how did I know that that's negative 1.3 repeating? Well, let's be very clear. Negative 1.3 repeating, it's really equal to negative 1 1/3. All right, so that's the first thing I want my student watching to know. Now, how did I know that that's negative 1 1/3? I think what I want to do for the purposes of this video is only say the following, which is kind of like a rudimentary way of understanding the situation. Um, it's negative 1 in this direction plus a fraction. Okay, so it's negative 1 in this direction plus a little piece of this whole thing. So I'm asking myself, well, how far into this whole thing are we going? Now, the way I knew that it was 1/3 into this square is because if I go from here to there and I consider how far up we're going, right? There's 3 squares up, and it goes 1/3 of that distance up to that moment. All right. So in other words, I'm kind of investigating this blue segment, and if you consider up and downness, it's going 1/3 of the way up and then 2/3 of the way up. So that means it must also be going 1/3 of the way over and then 2/3 of the way over. All right. So I'm hoping that clicks with my student. There's a more painstaking way of going about finding that negative 1 1/3. I'm hoping that that is sufficient, though. Okay, y-intercepts. This one right here, that would most definitely be 0, comma negative 1. The relative minimum, so that is, how far, what's the lowest point that it goes when we kind of zoom into this section? Now, the reality is it goes down forever, But there's this kind of moment where we clearly see like a valley, So when they ask for the relative minimum, they're asking for the y value associated with this low point. And the y value associated with this low point is negative 1. Relative maximum. Well, you actually have 2. You have this one and you have this one. I actually think you should talk about both. We have a relative maximum here at 3 and another relative maximum here at, this was at 2. Whoops. So let me fix that. But the other one was at 3, right? The other one is at 3. So the first relative max is at 2, and the next one is at 3. Okay, evaluate f of negative 2. Now, whenever you see this function notation, what this is code for is the following question. When x is equal to negative 2, what does y equal? Okay? So for my student watching, you might want to write this and throw this in your note card. Okay. So let's find out. When x is negative 2, okay, x is negative 2 here, what does y equal? Well, let's go up to the graph. Y equals this, right? We traced when x is negative 2. What does y equal? Well, find the y value associated with that point on the graph. So that's a 2. Okay. Find x when, okay. This is another one that might require some translation. Anytime they ask a question like this, you can translate it by saying, what is x when y is 4? That's the question they're asking. What is x when y is 4? Well, let's take a look at when y is 4. Well, when y is 4, um, it's up here, and the graph doesn't even hit that. So to me, that is a very annoying question. Okay. What is x when y is 4? I don't know. At the y value of 4, the graph doesn't even go up that high. So x does not exist, or we could say, I don't know if we should say undefined. Maybe. What I would say is this. I would say there is no x value such that f of x equals 4. I think that's what I would say. All right. Now, for my student watching, imagine they asked a different question. Imagine they asked the following question instead. Imagine they asked, find x when f of x is equal to 1. Well, what you could have done is you could have investigated this y value of 1 right here, and maybe even drawn a line across, and then just find out where this thing crosses that line. It crosses at these red points, right? And then you would just have to find the x values associated with those red points. So you would actually have more than one answer to this question. The first x value would be this 3. The next x value would be like this negative 1.5 looking thing, or negative 1 2/3 looking thing. The next one would be this 3 1/3 looking thing. Okay. So negative 3, negative 1 1/3, and positive 2 2/3, which is really 6 repeating. So that would have been the answer to that question. So I hope that makes sense. With regards to the note card, my thought is to literally kind of put this information there, and I'll show you, I'll zoom in a moment. I would put this information in the note card in the sense that you kind of want the ability to translate this annoying question into a real question. And you want the ability to translate this annoying prompt into a real question that you kind of wrap your head around. You might want to, put those samples in your note card. But anyway, hopefully that makes sense. Hopefully that was helpful for my student watching. Good luck. And for anyone else watching, good luck with any test that you have as well. And I will talk to you all later. Bye.